Hi, my name is Andreas Hinterreiter. I'm a PhD student at Johannes Kepler University Linz, and in this video I will present ConfusionFlow. ConfusionFlow is an interactive visualization that lets users analyze and compare the performances of multiple classification models over time. To this end, ConfusionFlow introduces a novel temporal adaptation of the traditional confusion matrix and pairs it with line charts for precision and recall. ConfusionFlow was a collaborative effort with my colleagues Peter, Holger and Martin, at the time all at JKU Linz, Jürgen Bernard, who was recently appointed assistant professor at the University of Zurich, Hendrik Strobelt from IBM Research, and my PhD supervisor Marc Streit. First, I'd like to talk a little bit about why we saw the need to develop ConfusionFlow. Classification is one of the most important machine learning tasks, and it's already applied in a wide variety of real-world problems. In recent years, the demand for model interpretability and model explainability has grown a lot, and one way to better understand a model is to carry out a detailed performance analysis. Visualization has grown increasingly popular for this kind of tasks related to explainability and performance analysis. Yet, when we looked at the problem of analyzing how classifiers perform, we found that there were some gaps yet to fill. The development workflow in machine learning can be seen as iterative and incremental in two senses. On the one hand, model developers constantly need to tweak parameters of their models, trying to improve them, re-evaluate them, and compare the performances of multiple models. On the other hand, the actual optimization loop is iterative as well, which gives rise to a temporal analysis axis, because the model states change over time. A fully detailed performance analysis of classification models includes temporal and comparative analysis at the same time. We also realized that the performance analysis of classifiers can be carried out on three different levels of detail. On the global level, aggregate scores such as accuracy measure how well a model performs in terms of a single number. On the class level, there are aggregate scores such as precision and recall, and other constructs like the confusion matrix. Finally, if you want to analyze how your model performs on an instance level, you have to look at individual ground truth labels and predictions. Now, if you want to adapt your analysis to also cover the temporal aspects of the training, this is easy for the global level. You can simply plot the single number scores as line charts, which is exactly what is done in many performance analysis tools. However, on the class level, tools previously missed out on the temporal aspects, and this is exactly the gap we try to fill with ConfusionFlow. We introduce a temporal adaptation of the confusion matrix that allows these temporal as well as some comparative analysis tasks. At the end of my talk, I will also come back to the instance level and talk a little bit about how this can be extended to cover temporal analysis tasks. Before I explain how we adapted the confusion matrix for ConfusionFlow, here's a quick recap on what the traditional confusion matrix includes. The rows are the ground truth class labels of the data, and the columns are the predictions. Each data item that is really of class A, but predicted as class B, will contribute a value of 1 to the cell for the AB class pairing. You can also see how the class-specific precision and recall can be deduced from the traditional confusion matrix. Now let's assume that we have a confusion matrix for each iteration of the training loop. For the ConfusionFlow matrix, we simply bring together all these matrices in such a way that now a single value is replaced by a temporal line chart of the confusion. Now if we want to compare multiple models, we can simply add additional line charts for each model. Since this visualization can be a little prone to visual clutter because it uses overplotting, you can also transform each line chart to a heat map where time progresses from left to right. And instead of overplotted lines, you can stack those heat maps to form so-called lasagna plots. This gives rise to the second version of the ConfusionFlow matrix that uses the heat map encoding. Here you can see how the actual implementation of the ConfusionFlow matrix with its two different encoding options looks for real data. On the left you can see the line chart encoding, and on the right the encoding that uses stacked heat maps. If the user selects a single epoch, and I will show you in a second how this is done, the line chart's encoding also shows the confusion values for this specific epoch as a background heat map. These are the gray bars that you see on the left. Let me now show you how the ConfusionFlow matrix is incorporated in our visual interactive prototype. The performance logs can be selected up here. Let me just select two. You can see that each model is automatically assigned a unique hue that is used consistently throughout the whole visualization. On the left you can see the ConfusionFlow matrix, and I can switch from the heat map to the line chart encoding, or increase the contrast. Each cell of the ConfusionFlow matrix can be brought to the detail view here to the right. Same is true for the precision and recall plots that are shown up here. If I'm interested in only a subset of the epochs, then I can change the selected time range using this epoch slider. I can select individual epochs by clicking the epoch number, and as I explained earlier, the confusion value for this epoch will be shown in case of the line chart encoding. To evaluate the usefulness of ConfusionFlow, we conducted a case study with our collaborators who are working on active learning. Since labeling datasets is an expensive process, active learning tries to minimize the number of data items that need to be labeled manually by carefully selecting which item to be labeled next. This is done using different selection strategies. The model is then re-evaluated after each instance, and then the next instance is chosen. This creates a very fine temporal granularity. And the fact that our collaborators wanted to compare different strategies made this scenario a very fitting one for ConfusionFlow. I cannot go into detail about all the different findings that our collaborators made. I can just let you know that they were very surprised how the confusion patterns varied over time and between strategies. In the ConfusionFlow matrix on the left, you can see that in many cases, a single time step causes a huge drop or increase of confusion. Our collaborators liked the fact that ConfusionFlow is based on familiar visualizations, like temporal line charts of performance metrics and the confusion matrix. They said that this helped them to quickly navigate through the information-dense display. They mentioned that ConfusionFlow motivated them to perform an in-depth analysis, but in order to truly understand all their observations, they saw the need for an instance-level analysis as a follow-up. Since the confusion matrix grows quickly with the number of classes in the dataset, we also carried out a detailed scalability analysis of ConfusionFlow, where we compare different strategies to cope with the increased number of classes, such as class aggregation and class selection. In the paper you can also find a use case that deals with neural network pruning, where the network is allowed to change its architecture over time. From all our evaluation use cases and scenarios, one of the most important insights was that the confusion matrix tends to become sparse and noisy as the training progresses. This makes it very hard to identify true patterns from looking at just an individual snapshot of the confusion matrix. The temporal analysis tasks enabled by ConfusionFlow make it possible to identify true and stable patterns. But we also realized that for a true and deep understanding of models, ConfusionFlow alone is not enough. It needs to be in conjunction with other tools where it can serve as an analysis springboard. One such tool, and now I'll come back to the instance level that I talked about earlier, could be InstanceFlow. InstanceFlow is a tool that lets users analyze the temporal progression of instance level predictions, and it was accepted as a short paper for this year's Viz conference. If you're interested in InstanceFlow, you can check out the talk by my colleague Michael in one of the short paper sessions. If you would like to find out more about ConfusionFlow, A preprint of our TVCG paper is already available online. You can also try out a prototype implementation yourself by visiting confusionflow.kaleidoapp.org. ConfusionFlow is open source and you can find the source code on GitHub. It's also pip installable, which should make it very easy to try ConfusionFlow on your own data. And with that, I want to thank you for listening.